I think we're gonna start. If we're not gonna start right now, I'm not gonna make it till 11:30. All right. So hello everyone. My name is Paweł Szulc, and I'll be making a talk about free-monad. So when 2 days ago, John asked me if I could do a presentation for him, I answered, "Oh my God, yes." I should probably be more cool about it, like, let me just check my schedule. Yeah. But anyway, he asked me what the talk might be about, and I've reckoned free-monads would be actually a good thing to talk about at a Scala conference. The one reason would be free-monad is right now a cool thing. Like, it's really hard to go to a Scala conference around the world and not see a presentation about free-monad, to the extent that I'm scared right now to open my fridge because I will see a free-monad. But the main reason I wanted to do the presentation was that I've been working for the past 8 weeks on a project, pure functional, which they use free-monads to the very extent. And I always like to talk about things I've learned, so this is kind of like a drop of the knowledge I have about free-monads. It doesn't mean I'm really knowledgeable about them, but I hope be able to answer some of you guys' questions. So the general outline for the presentation is I want to explain what a free-monad is. There's really two ways to talk about free-monads: how they are implemented in a given language, Haskell or Scala, or what's the notion, how we could really think about what a free-monad is. And this presentation is more about the notion, the concept, not really about mechanics. I mean, we're going to see some of the mechanics, but not that much. So the code I'm going to be using is Scala Z, but if you prefer cats, if you work with cats, for example, the general concepts are exactly the same. The mechanism might be a little bit different, but internally, not in the higher level. And also, I've seen some question about free-monads. People see those like initial presentation of a free-monad is, and they answer some questions, and I hope to answer them as well. It's like answer questions from Twitter. Yeah, and that's a general outline. But before we start the presentation, I also wanted to touch a little bit the motives. Like, why should we really care? What's so different about free-monad? Why would I really even consider using it in my program? So before we start talking about free-monads, let me just quickly touch that first topic here. So can anyone tell me at the audience what functional programming means? Like, what's the definition? I've heard programming with functions, but in a way then Turbo Pascal would be a functional programming language, right? They're a function as well. On the internet, I've read there are no assignments, no variables, once given a value, never change, and no side effects. So it's always like no, never, no. And I once read this paper, the guy said, like, functional programming sounds rather like medieval monk denying himself the pleasures of life in hope that it will make him more virtuous. But there's something to a functional program, really, and it's a thing that we strive for modularity. If you think about any cool thing that is happening in our industry every other decade, microservices, so object-oriented architecture, object programming, actor model, we get very excited about those things because what they provide really is divide and conquer ability to tackle the problems that we have. We have something complex to write, we divide it into some sub-problems, we solve the sub-problems into sub-solutions, and then we need the way to combine the sub-solutions together into the final solution, right? And functional programming, it's actually, you can trace that back to a conference which happened in 1968. It's the conference that they first actually coined the word software engineering. That's the first time they actually use it. And one of the panels was driven by Dijkstra, and he was actually talking about that, at the beginning of the 70s. So we've been looking for that way to divide and conquer. We've been looking that way to tackle the complexity of our software almost since the beginning of our industry. And if you really think about functional programming, that they kind of solves that problem, right? You have an input and output. That's what your function really is. It's a mapping between input and output. And you can test it. There's you can think of them as modules, and then you can combine them together to reason right now about something more complex. So in a way, the functional programming is really cool, right? It gives us that ability to actually divide and conquer. So now the question would be, where's the hatch, right? Where's the catch, sorry. And there's this awesome comics I just love. So the lady is like, a code written in Haskell is guaranteed to have no side effects. And the guy is, because no one will ever run it. And that's the thing about functional programming. Like we like the idea of modularity, we like the idea of isolation, but we kind of fear that how it's going to work in a program that is really, really complex, in a software that is really, really complex. Can we actually use it? Like, what are the mechanics? And free-monads is actually one of the ways in functional programming world to actually have that modularity, have that isolation in a way that it's easy to grow, to scale while our software is growing. And so that's the motivation for this talk. We shouldn't really learn about free-monads just for fun or just because it's cool, but just wanted to just give like an outline why that might be important. So a free monad, that's basically the type signature of a free monad. You should think of free as a program. This is basically your program. And that program uses some kind of language, so that the language defines some vocabulary that you use to create your final solution. And that A over here is just a type of the value that your program is gonna calculate. That's basically it. So if you think about languages, if you think about your programs, you have your program, but then you also need to run it, right? So just having that instance of that type doesn't really give you anything. You still need to have something that will run your program, and that something is called an interpreter. So you need to have a way to interpret your program. Now, the thing is, I've been asked, John asked me to do this presentation 2 days ago, but I only had like 24 hours to prepare it, so there are no more slides. The rest is a code base. But fear not, I will not do live coding because that never works. What I have is a growing repository of commits, so everyone compiles, we should be just fine. All right, so can everybody can see it, the font. Is it okay? So this is, we define slowly as this language of ours. So the language, they sometimes call it algebra, and I might be using interchangeably. So the algebra here is input-output, and we define, so the vocabulary will be print line and get line. And that's basically it. So we say that if you want to print line, you provide that line, and the program will calculate the value being calculated is just unit, and if you get line from somewhere, it will give you the value that we get will be a string. Now we need to have a way to actually lift this language that we define to our programs, and the easiest way is to use this helper function here, lift-f. So essentially what it does, it takes your algebra and lifts it into a free program. So already here we have two functions, printline and getLine, which they produce a valid program that the first program over here will just print line, and the other one will get that line. And now if we move a little bit further, because that's just not enough, we should see here our first program. So now because a free monad is a monad and we can use for comprehension, now we can actually write something a little bit more complex. This is probably something you've written in C or Turbo Pascal back in the day. So what's your name, right? You provide your name, and then the program will output, nice to meet you. That was fun, right? Writing those programs. But if we would actually, if we run it, come on, nothing really happens, because as I said, it's just a program. We still need a way to interpret it. We just define using that syntax what we want to do in our program, but we still don't have an ability to run it, and we need that interpreter. And as I said, it's already here. If I could only, you know, code like this at work, that would be so cool. Yeah, so the thing that we have is this. So now we have a console interpreter, and this is an object that extends something which is kind of looks pretty weird. And as I said, there's not going to be many mechanics, but the ones I will show you, you can find them both in Scala Z and Cat. So they might have different names, but they are more or less the same. So if we go to, sorry, maybe I already have it, yeah. So the thing that we're looking at is called natural transformation. If we really look for it, it's it's something like that. So you can see that this weird operator is just a natural transformation from F to G. So this is exactly the same thing. And what it really is, the natural transformation, what it really is just a function. So you should really think of it as a function of, F to G would be, it's exactly the same as F of A is a function F of A to G of A. That's what it really is. So nothing else. And that's why this operator here is nice, because you can think about it this way. So now we provide interpreter, so we have to provide that function. So for our given algebra, for our language, we want to provide a separate thing. So we want to have something being produced. And here I'm using a task. Task is if you don't, guys, who knows what a task? Maybe who doesn't know what a task is? Okay, so think of a task as a future, so like a future plus plus, in a way that it pretty much the same, but the thing is it doesn't really run when you instantiate it. You instantiate task, but there's still a separate method that you have to call to actually start the calculations. So here we're just saying, all right, so if the input and output is a print line, what we want to do is just want to print that line to console, and we close this over task. And the same way, if we encounter a get line, what we will provide is a task that will essentially read that line from the console. Now since we have that, we can actually run our program. So we call a method fold map, because if you look at how free is implemented internally, that's what it actually does. It folds down the structure, and while folding, it's mapping using that function that you provide, so that interpreter. So after we run our program, we get a task, and at the very end, we can run this task. And now you will witness something which is really cool, because that will be, back to the basics when we, reload. So what's your name? Paweł. Nice to meet you, Paweł. Yeah, this is so awesome, right? Not really anything complex can be written with it, right? But anyway, let's move on. So one of the things people talk about free, which is really cool, is the ability, not only the modularity and isolation, but also ability to test it. Because if you really think about it, how you could test your program, which is written in such a way, right? You actually put some stuff to the console and read some stuff from the console, and that's one cool thing about working with free, that you can have your interpreter, production interpreter, like the one we just created over here, but you could also create a different interpreter for your unit tests. I know not everyone is really fond of unit tests. Some people like to run integration tests, so maybe that's not a benefit for you, but people who actually like unit tests, this is something they might consider a cool thing. Because if we now look at our specs, what I did is not really pure functional implementation, but then again, I was writing it, I think, at 2 a.m. in the morning. So anyway, the idea is that I provide the input and output for my interpreter. Those are both mutable collections. And the interpreter goes like this. If you find a print line that somebody's printing stuff in their program, just put that into that output. And if somebody wants to actually get a line from in their program, just pop the stack, take the first element from the stack. And now that program we just ran a second ago, we can actually test it, because we can provide the input, the empty input, and the output with input with things that we will push into our program while it's running, and the output will be empty. And now we can run our program. This is the same program that we have in production ready code, but we run it with different interpreter. So now after that program has run, we want the input to be empty because we want everything from the input to be actually read. And we want the output to be like, what's your name? And then, nice to meet you, Paweł. And that's basically it. So that's a nice feature, and that's a nice ability to reason about your code. And you're just cutting all those effects if you don't really want to deal with them in your tests. If you want to, then you can, but you just can just. This is the best way, I think, to write a unit test. But anyway, that wouldn't be really that exciting because. Maybe just one more thing. Like one of the patterns that I've seen is that some people tend to, if they have functions like printline and getLine, at some point they realize they have like a little bit more higher level constructs, like for example ask, which would be a printline and then getLine. So my program is now over here just a single ask that prints that stuff to the output and get it from the input. So that's one of the things people do just to get rid of some of the boilerplate. Now, I added additional example here, which is called logging. And I'm just gonna like quickly go through it. It's because it's exactly the same. We one more time define our algebra with info, warn, error, and debug. We provide ability to live that algebra, to live that language into a program. So to program with a free of that algebra, and then we can write in just some dummy interpreter here, which loses log4j. Basically, does what you hope it would be doing if you have an interpreter for logging. And then you can run your program, and then, I mean, I can show it. It's just gonna work, hopefully. So if you run it, it produces the info and the debug that we were hoping to have. Now, this is cool, right? But in a way that if you can imagine, if you have a more complex solution, writing like a whole big language for your final program, like a big algebra, big language having consisting everything, would be just crazy, right? Even here we see different concerns because logging and input and output interaction with a user is something completely different. So, and I said free will provide you this isolation and also modularity and composition. So the question would be how we could achieve that. And the answer is near. So what you want to have is this. Okay. So what we want to create is we want to create a type, a new type, which will be a co-product. And co-product, actually I can show you the product. Co-product is nothing else than just an either between two types. They used to be functors. Now they don't have to be functors, but they just have to be higher kind of types, and that's just it. So you think of it. So think of it just like as like a union. Right now we create a new type, which is a union of our input-output algebra and of our logging algebra. And we would like to write a program that would use that language, that language that is composition of those two languages that we've defined separately, the two separate concerns combined together. So that's the thing that we try to here achieve. So now that's what we will be doing. Now it's just preparing. So I made some changes right now to our input and output, and it looks right now a little bit different. So right now it used, as you guys remember, it used to be the free of our input and output, right? And now it's free of some s. It's not our input and output. And the question would be, what that s is? What the hell? And we have the notion that our ops here is parameterized by that s, but there's also additional constraint, we say that the S is as such that input and output is injectable into S. What that really means, I can later on show you the mechanics behind it, but what that really is, it means, think of it this way. S is a co-product, right? It's some co-product. You don't know what that is at this point. But not only it is a co-product, but it also, one of the elements of that co-product has to be input and output. So it could be it could be co-product of input and output and something, but at this point when you define it, you don't really care. You just constrain it to be co-product of a something and your input and output. That's so you guys probably see that here we have that co-product, right? Of input and output and something else, right? This example is just logging. So now we the difference here is that really we have to use it's the thing that's defined here is called inject. In Scala that you want to look for inject, and that's really what it is. It's just this class, and there's just a type. You see, this is exactly the same. So now almost everything looks similar. The only difference here will be when we define those helper methods, we not only lifting our language to free, but before we do that, we also have to inject it to that S, and that's the only difference. Now, if we look how our program is defined, it's still the same thing. It's just exactly the same how it looked before, and our interpreter is pretty much the same. So nothing changed that much. And if we look our login example, the changes that we made were exactly the same. But this time we're saying, right now, you will create a program whose language is S. And what S is a co-product of logging. So it's a union of logging and something else. At this point, we don't really know what that is, and we don't actually care what that is. Having that, so everybody's good with that explanation, because that's actually foundation for what I'm going to show you in a second. Who's confused? Who doesn't understand what I'm saying with the Eastern European accent? Okay, everybody should be fine. All right, so now, oh crap, don't fetch. No, fetched. That's the problem with shortcuts. They tend to. Never mind. Okay, so now what we will now have is if we go to our program log and console. Now since we redefine the way that we have those helper methods in those classes, this ops class, right? We can now say I have a program, and I need in implicit scope instances of those classes, those helper methods. So just to remind you, instances of this class, if they are in implicit scope, then I can reuse those methods, right? I can have those helper methods to instantiate the basic programs, and so I can compose something more complex. So now, if I have instances of both those two helper methods, I can create a program, final program, whose language is going to be S. And what that S is? Well, the S is constrained here, right? One was saying S has to be a co-product of input and output and something else. The other was constraining it has to be a co-product of logging and something else. And that's exactly what our EFF type is, right? It's a co-product of input and output and logging, right? So this is exactly what we needed. But really at this point, we are not yet using that EF type. We're just still constraining our program, and we are saying, it will give us a program using that S, and there are the constraints what that S has to be. And now we can log and ask for a name and maybe put that name into debug for whatever reason. Now the question would be how we could write an interpreter for that program. It wouldn't be really that nice if we have to re-implement it one more time, right? We already have interpreter for login. We already have interpreter for input and output, for I/O. Would be nice if we had ability to combine those two together. Now the thing about Scala Z, they actually don't provide such operator. Cats has it. It's called OR. Scala Z will have it once I push the stuff I've written to Scala Z, but I'm a bit scared of committing because it's like doing this for the first time. Anyway, if you're using cats, you already have that operator, and but if you don't, you need it. And if you're using Scala Z, so that operator is here. So it basically enriches the natural transformation. We add ability to combine two interpreters together to create an interpreter for a co-product. So now, if we look at our interpreter, what we want to have is ability to interpret that language, that EFF, which is a co-product of input and output and login, and we want to the final value that we want to have to have it closed over a task. And that now you can just reuse our previous interpreters that we've written a moment ago with that OR operator. If you're on cats, you will do OR. That's the only difference here. And so yeah, so if we actually reload and run it, this would be login console. So what's your name? And that is, it gives me that value, and also that value, the name was Paweł, is put to the logger. So now we have ability to reuse, so combine this together. And it's really something nice, because now think of it really. If you have different consents, think of your application. A simple scenario where you have a user who needs to transfer money from a bank account. You will have authorization, you will have some storage mechanism, you will have different consents of your application, and now you can reason about them separately, and then create a final language which would be just composition of those different concerns. But it's not really that easy, and I will show you the example where that thinking actually might fail sometime. So yeah. So now we will go here. So what I've provided is yet another. How much time do I have? Oh, we're good. 15 minutes, right? Yeah. Probably, yeah. So we're good. So now there's yet another algebra. Go away. User account. Yeah. So yeah. So that's the algebra where we have a vocabulary like create account, update age, deactivate account, delete account, and fetch account. And when you create an account, the thing that you are, the value that you will be given is a handler. Handler is just an ID. It's a long to ID to the user that you just created. And then you reuse that handler whenever you want to update age, deactivate account, delete account, and so on and so forth. And now, actually, let me show you something I had, which is already here. Yes. So now, if you think about it, if you look at the program, so it's a user app 1. From the user perspective, this actually looks quite nice. So here I'm writing a program using a language which is a co-product of I/O and this manipulate account algebra. And what my program is doing is asking for your login, asking for your age from the input and output algebra, and then creates account. Oh, there's an error. Should be an age. Yeah, just like that, right? But I'll just leave it as it. But you just think of it. Here should be an age. This is probably a commit from 3 a.m. in the morning today. And at the very end, we fetch that user from our manipulate account, and we return that user account class as a final output of our program, which is obviously closed over option because somebody might ask for a user who doesn't exist for a given handler. So from the perspective of how you define a program, it actually looks quite nice. This is what I've been talking about, right? Isolation. You have the different algebras which you can test, and they work together if you combine them together. However, if you look how it's defined, and if you look at the interpreter because the interpreter here is, one more time, composition of existing interpreters, So here the console interpreter was just lifted so that this interpreter returns a state monad. So the other one was lifted to also return a state, and so those two could be combined together. So our final output returns a state which we then run over initial state, and then that gives us a task. You will see in a minute, because if that's confusing, it's confusing for a reason. And that reason is here, user account. Because if we look at the interpreter really, what we do is we interpret from that manipulate account language to something that I called storage state. And storage state is, because if you want to reason about our program, we'll need two things. We need the ability to initialize that ID, right? Because that's the thing that's going to be returned, that handler. It's a long. We have to create it. And also we need ability to somewhere store our user, so later on we can retrieve it, right, or update it and whatever. And this implementation here just reuses long for creating a value, and it uses like an immutable map. And since we want to have this solution in a pure functional way, we just use state monad to. So we're not really having that state where we define our interpreter. We sort of create a recipe. Once you give us initial state and run it with initial state, this is what will happen. But now this interpreter is rather crappy, because now something that a moment ago looked nice now looks horrible. Why? Because we are actually mixing concerns here. We have something which is really high level, like user manipulation and some logic. That logic really isn't really that complex. Deactivating user is just making a flag inactive. Active equals false. But if you really think about it, there are two different things. I'm doing some business logic over here at this point, but there's a lot of code that has to deal with this way how I store my things, how the ID is being generated, how the things are being stored in state and stuff like that. That's not really nice if you think about it, because this is still a very simple example, right? You think of the programs that you do in your daily job, right? It probably is a lot more complex than that. So this could actually be quite a hell. So now people ask over the internet that is there ability to not combine programs together, but sort of stack them one on top of the other. And there's actually such a way. And this is what I want to show you guys. And it's over here. So before I show you how it's actually done, let me quickly show. So I've added two things, and we will just quickly go over them. So the first thing is a key value store. Where are you? Here. Key value store. This is one more time algebra with a language like get, put, and delete. And this is the stuff that we've seen before, right? It has its interpreter. It just works. Just think that it works if you. The source is on GitHub, so if you want to reason about it, you can later on offline. And we also have, so we have a language that allows us to put stuff into some kind of storage, retrieve it or delete it from that storage. And we also created something which is called monotonic sequence. And monotonic sequence has a very simple algebra. It's just a single element next, so it will just generate us a next long value that we can reuse. All right, so these are two one more time languages that we can use. And now the question is why we would do that. Okay, so I'm not going to actually take it. Just you see, like there's rename between interpreters to MA interpreters. So if somebody's confused, that's this comment. So we're just going to jump over here quickly. So now what we're going to do is we're going to go to user. I had somebody yawing, so I'm really close to the end, no worries. So now what we're doing is we have this program looks exactly the same as the previous one. So if we actually open the previous one here, user app, you see that sorry. Okay. The program that we define is exactly the same. Nothing changed between how we define our program. The difference is between the interpreters. So now the program stays exactly the same. However, now our interpreter for manipulate account, if we open it, this is the one. So here's the trick. Before, we were interpreting from our program to a concrete value, like a task or a state monad or a closed over task and stuff like that. Here we're doing something different. Our interpreter interprets our program to another program. But that second program uses a lower level language. Think of it as compiling your program, your high level program, Scala, to lower level program, bytecode. That's exactly what it is. So now we put all the concerns of how we store stuff into key value store, and we put all the concerns of how we initialize next long to monotonic sequence. Now our interpreter here is only concerned about higher level logic. What does it mean to create a count? Well, you store it. I'm not telling you how at this point. I'm not telling you the mechanics behind what that key value store is. It might be anything. It might be your JDBC connection behind it. At this point, I don't really care. What I'm saying is you just create an account with a login and age, and you are giving a handler from monotonic sequence. And if I'm gonna deactivate account, it's really just taking that value from key value store, updating it the active flag to false, and putting it back to key value store, and that's it. So now I have one more time sanity. I can still not only I have modularity and isolation, but I can also reason about my program without my mind blowing, like what the hell is going on? Because this is nice. This is just the level of abstraction that I need at this point. I will have separate key value store interpreters and monotonic sequence interpreters as well. And the also cool thing is that I will write interpreter for key value store only once and for monotonic sequence only once. So if I'm writing those programs, many people say that, oh, free-monads are okay, but there's a lot of boilerplate. Where there is, but you can actually deal with it. And that's one of the ways you can do it. Because you can reuse the interpreters for those languages, and because that's like a low-level language. You just define an interpreter once, and so like a bytecode, right? The JVM knows how to interpret your bytecode, and then you can write your programs using Scala, and the lower-level mechanics are exactly interpreted always exactly the same with the same mechanics. So now if we jump to our user app, we see that we have our program that works on that EFF. So our first interpreter that we want to create, or maybe I will just show you. So with the how much time? 4 minutes. Okay, this is crazy. Okay, so the interpreter for account manipulation needed, as you guys remember, needed key value store and monotonic sequence. And the interpreter for our console just needs a task. I can show it to you, but just take my word for it. It just needs a task. That's the only constraint that it has. It also compiles. It's better if I show it. So that interpreter also compiles down to it's over here. Sorry. Also compiles down to a free, which uses a language S, but we only put one constraint on it. That S is a co-product that has to have task in it, and that's the only constraint that we have. And now the first interpreter that we're going to have from our EFF will interpret our EFF to a lower level language. That language, which is S, has the following constraints: key value store, monotonic sequence, and task. The first two come from manipulate account interpreter, so from this one. The task comes from the first one. Now, if you have type level Scala compiler, this would actually be nice, easier. It would just write interpreter or the second interpreter. But because of the bug that was recently fixed, but I don't have that plugin here. You have to do that little trick that you see. But then you know, if you have that plugin, this would be just a one line of code. And now we have an ability right now to interpret our higher level language to a lower level language, and then we defined yet another type, so lower level effects. Now this time is a co-product of task monotonic sequence and key value store. And so now we actually need an ability, and this is not implemented because that seriously was 4:30 in the morning today. So apologies, no implementation for it. I will provide it if anybody is actually hoping for that implementation. I can do it on my way back home. But anyway, the final interpreter, and we'll just use a composition, because interpreters, which are those natural transformation. In this case, remember natural transformation. They have, as you can see, compose and then. So you can compose and compose those interpreters from, and the final interpreter will go from our higher level language to the final thing that we want to actually evaluate, calculate. And what we're doing here, we're just saying, you know, first interpret that to the lower level language, and then having that program interpreted that program to just the final thing that we want to calculate here, which is task. Any questions so far? Yeah.
When your intermediate, like I think it was inline interpreter, one that had a dependency on two other interpreters.
Which one?
Is it inline interpreter?
Oh yeah. Okay.
So it's got a dependency on the monotonic sequence.
Yes. Yeah.
So say the KDS results in a task or state monad, and the monotonic is a state monad.
Yes.
What if you wanted to get access to monad operations inside the interpreter? Say you wanted to publish an event, so you wanted to access a writer monad inside that.
Well, you could still do it, but not the way how it's implemented here. But you have the ability to you will just write a different lower level language, and that would just work.
So you have to call out to another interpreter?
Yeah, but I don't think you really need that, because you want to. So the thing is, you want to reason at this point. You don't really want to know how monotonic. Yeah, but the monotonic sequence, the interpreter that I have here uses state monad, and a key value store. Well, it doesn't, but anyway, it could. And the thing is, you don't really want to know at this point what's internally there, because for what you can know, the key value store could be just your Mongo if you're crazy. You know, whatever you want, right? So, and at this point, you really don't want to have the ability to go into the details of what the interpreter does. Yes.
Sure, but in the actual, say I've got handler there, say I've got ms.next handler, and then I wanted to just publish an event which said, I've got a handler and it's this value, just or a logging event or something like that. And maybe that would go into, say, a writer monad. So now you've got a stoic one that could have a monadic kind of dependency as well. I don't know if you can get that in there.
I don't know if maybe we could talk about it at the presentation, because maybe it would be easier with Codebase, so that's okay. I have, I think, 1 minute, which is good, because that's all I wanted to show you. Anyway, quickly, the resources. This is the paper where Runar was showing how this is implemented internally, which is quite nice. Data types a la carte there's some tricks that we were using, and some of them that were shown here. Some videos. This one, why the free-monads isn't free. It's actually the nice explanation. The only difference I don't like about it is at the very end when she says it's really isn't that cool. I think she's wrong, but that's my that's my thinking of it. Yeah, and there's some other blog posts if you prefer blog posts. And last thing is, if somebody was asking me like where's the real usage. So the company sorry, you're making a picture. So the company I work for right now, they make a product which is called Quasar, and there's a link on the next slide, and it's completely open source, and they use it at the very extent. So that they do what they do is they have a sort of like a language, like a superset of SQL, and then it compiles down to different storages, and they use free to the very extent. And also, if any of you were on the fixed point presentation, those are the guys who are behind Matryoshka, and fixed point data types are also used here to a very extent. So if you're interested how that can be actually used in a bigger project, and you just want to see is it really that cool and that easy to reason about your code, this is the place to go. My name is Paweł Szulc. This is a Twitter to complain. And the last link, this is actually the repository, and you can follow all the steps that I just did 30 minutes ago. Thank you very much.